Welcome to Closer to Truth. I'm speaking with neuroscientist Terrence Sejnowski, author of the vital, timely new book, ChatGPT and the Future of AI, The Deep Language Revolution. Welcome, Terry. It's great to see you again. Last time on Closer to Truth was more than 20 years ago, 2003.
That's right. It's great to be back.
Great. Anything happened in the world since we last saw each other?
Well, it's really been a ride here, but I've really enjoyed it.
Great. Well, me too. It's not all been good if you read the daily newspapers sometimes, but much of what you've been doing in the science world and neuroscience and AI is really remarkable, and we'll get into that in great detail. At least you and I haven't aged very much over these 21 years, so at least that's good.
Well, we're still kicking, that's for sure.
I'm really looking forward to our discussion. I love the book. Before we dig in, just an opening quick question, and it's from your book. Why did large language modules shock the engineers who created it? I understand shocking the general public. I was shocked when it first came out 2 years ago. But why the AI engineers themselves?
Well, the applications that had come earlier were for specific problems like object recognition. What's amazing about these large language models is that they can do many tasks. In other words, they're much more general, answer many different questions, and the generalities surprise everybody, including me.
Okay, let me give a brief bio, a proper bio, and then we'll dig in. Terry Sejnowski is a distinguished computational neurobiologist, recipient of the 2024 Brain Prize, pioneer at the intersection of AI and neuroscience, Francis Crick Chair at the Salk Institute for Biological Studies, and distinguished professor at the University of California at San Diego. He is the president of the Neural Information Processing Systems Foundation, which organizes the largest AI conference, and he is a leader in the convergence of neuroscience and AI. So, Terry, let's begin by talking about, in detail, how large language modules work. How do they, for example, differ from our legacy computer, algorithmic logic, and traditional search?
So, first of all, compared to the traditional approach to AI in the last century, where you wrote a computer program for solving every problem, the magic sauce in modern AI is learning from experience, like we learn from experience, learning from data, large sets of data. And the larger the data set, the more capability these large language models have. So it's really transformed how we think about interface between humans and machines, right? Now we can talk. Before we had to use keyboards and we had to learn ourselves how to deal with digital computers. Now it's going to change over the next decade or two. You'll be able to talk and really treat your computer like you would someone, an assistant or somebody that you work with.
How about the conceptual difference between algorithmic logic and probabilistics, which are an inherent part of the difference?
That's really the key, mathematical key, was that if you're trying to base everything on logic, which of course they did back in the 20th century, rules, symbols, you're very limited because it's black and white. The world is not black and white. The world is shades of gray. And that's what probability is all about. It doesn't tell you it's yes or no. It tells you what's the probability of being yes, 50%. And working with probabilities gives you the advantage that you can deal with a complex world that is not just shades of gray, but shades of the entire spectrum, right? I mean, this is really a complex world that we're living in. That's the difference.
Okay. Now, how does that literally work when the large language module is learning on these enormously large data sets? Because we know that it's a really a prediction of the next word or the next step is all that's happening, all in quotes. And so when it goes and studies all of these billions, trillions of pieces of data, how is that learning stored?
Well, first of all, this is a neural network model, which is a very simplified version of the cortex, the cerebral cortex, which is our big knowledge store on the top of our brain. And what happens is that the information comes in and it goes through a sequence of layers where the information gets compressed and analyzed. And finally, when you get to the top, right, you get to the language part. But the key really is not as you point out, the architecture, but rather the fact of how it was trained. Previously, these deep learning networks had to be trained by labeled data. That is to say, you have given an image and you label it. This is a cat. And now it's using that prediction. It will predict the label, and it will then, if it makes a mistake, it will twiddle the weights, the connections between the units. They're like neurons, to make a better prediction in the future. And you keep doing that over and over. The beauty of these large language models is that they don't need labeled data. They just need data. And as you pointed out, the key is called self-supervised. It tries to predict the next word in the sentence. Now, that might seem like you do that all the time, right? You can anticipate what my next word is going to be. But it turns out that you can't really do that unless you understand what the meaning of the sentence, right? In other words, words are very ambiguous. There's a lot of uncertainty. But so the large language model, in order to be able to do that simple task, predict the next word, it has to create what's called a semantic representation. The meaning has to be embedded in the representation. That is to say, how you represent words inside the network now is going to be richer than just symbols. It's in fact, they very, very long vectors. Vector is a sequence of numbers that has to do with the different features in the word. So that's really where we are today. We've discovered that this very simple task actually produces amazing results in terms of the generalizability to many, many other tasks, not just the next word.
Critics have called large language modules stochastic, which means probabilistic, stochastic parrots, that it's just giving a probabilistic parroting of the data. Is that a legitimate critique?
Oh, well, it sounds like, that's a put down, but the fact is parrots are really smart, Irene Pepperberg taught a gray parrot named Alex to speak English, a parrot speaking English, and it could answer simple questions like, what is the color? How many are there? What is the shape? I mean, this is, parrots, why do you mean parrots? and sometimes I have to say, the critics sound a lot like stochastic parrots to me.
That turns it inside out. Let's get a very basic thing. ChatGPT, a GPT, generative pre-trained transformer. So those are three really critical concepts. That's not a GPT because it sounds nice at the end of chat. Each one of those words are very powerful, and together they really explain the whole thing. So just give me a quick definition of those three GPT words.
Good. Okay. Yeah, this is really critical. So again, the traditional deep learning network, you give it an input, you get an output, one output. And that's done a lot. I mean, it's in fact it won a Nobel Prize in chemistry, right, for predicting how the folding pattern of proteins. But generative means that it can generate one word after the next, just like humans, right? In other words, it's able to, by looping back on itself, it's able to answer questions, write, computer programs. It's really very, very capable in terms of generating sequences. And that's the G. P means pre-trained. So there are two different modes. During training, it's exposed to trillions of words, and it takes a lot of training. I mean, it takes months, and the most recent large language models cost hundreds of millions of dollars. Can you imagine that? Well, hundreds of millions of dollars. But it's really extraordinary that it can absorb that much data. So that happens up front. But then when you're using it, which is called inference in machine learning, when you're using it to get results, it gets the results really quickly. In fact, I was surprised. I mean, this is not just the answer it gives, but the fact that you press the button and you get the answer in 2 seconds, right? I mean, it takes me hours to write something like that, right? I mean, it's how did it do it? So that's the pre-trained. Now the real centerpiece is the transformer. The transformer is a particular architecture. Deep learning, deep means that it has many layers, and so transformers have many layers. But there's a couple of additional bells and whistles that were added. One of them was the fact that it had what's called a long input vector, which is every word that it says, that you say, and it says, goes into the input. So it has a running copy of everything that was said in to answer your question. And that gives it the ability to be able to take information over long, stretches. Just like, you have to remember what I said at the beginning, and I have to remember what your question was, right? Well, it does that by just holding on to it. So that's one thing. Number two is something called self-attention. Now, what does that mean? It's actually not what we call attention. It has to do with understanding the relationship between pairs of words. Like if I use the word "this" in the sentence, it refers to some other word, maybe in the previous sentence, and it could be 4 nouns. So it builds up by training. Actually, during the pre-training, it builds up a matrix of all possible associations between all possible words, and this helps it to be able to interpret and understand the meaning of the sentence, right? Because you take the context into account, of course, when we're listening to someone or reading, and that's how the transformer does it. It's doing it maybe in a slightly different way than we do it, but it's an important part of that process.
It's really so astonishing how successful the large language modules can be simply by predicting one step at a time, albeit with the training in the background so it knows the probabilistics of each word in context, but still.
It's astonishing. And it's actually, there's more and more evidence that humans use a similar type of self-supervised algorithm. And this is actually in another part of the brain called the basal ganglia, which is below the cortex, and there's a loop between the cortex and the basal ganglia. But we now know that the basal ganglia is important for what's called procedural learning. That is to say, learning a sequence of actions to achieve some goal, a reward. For example, it's used when you're learning how to play tennis. It's used in infants when they're learning how to talk, right? The language is during the first 2 years of life. I mean, this is amazing how quickly it happens. And it happens because this basal ganglia is doing this prediction. Predicting is called reward prediction error, right? It predicts whether the next step is going to be give you a good outcome or a bad, and it uses the difference, the prediction error, in order to update all of the connections, the strengths of the connections. So So this is a very important general principle that we discovered, and the brain uses it. Transformers use it. It sounds very simple. I mean, how could you get information out of that? It's just whether you did better or worse. But if you just do that every moment, you're building up an enormous what's called a value function. That'll say the value of a particular task, of a particular action that you're going to take. Is it a good one or a bad one?
Let me just ask some details about transformers. Some specific questions, very short answers. What is a token as an input? What is the definition of token?
Okay, a token, you can think of it as a word or a part of a word, or it could be a question mark. And what it does is it assigns for each of those tokens, it assigns a long, what's called embedding vector. In other words, it's not just a symbol. Words, we think of them as symbols, but in the transformer, it's a very complex sequence of numbers for the different features. And that's a token, like I say, it breaks down the sentence into little pieces.
And so a token is the most fundamental element that is used in the whole system.
That's right. That's the starting point.
Okay, so and we're going to have huge numbers of that. Now, you also talk about trillions of weights. So what's a weight that you have trillions of them?
A weight is the strength of the connection between units. So in your brain, you have these neurons, and you have connections between them, and they're called synapses. But some of those are very strong. They have a big impact on the neuron, the next neuron, and there are others that are weak. Now, those are the ones that we know in your brain are modified through experience. And in the case of transformers, there's an algorithm, a learning algorithm called backpropagation, which does that for the transformer.
Okay, I'd like you to know that over my left shoulder, if you can see that little purple thing, that's a pyramidal cell in the cortex.
Oh, right, I see it.
And to my right, you see a lot of brains of different animals. So, this is my area. I love it. Next question is the accuracy is sometimes, and the capability is determined by so-called flops, floating point operations per second. How does that figure in, and at what level are flops going on in order to create the large language modules, the outputs that we see?
Yeah, that's a really important point, because these training up these large language models takes enormous amount of computation. And back when I started working, I was a pioneer in developing these learning algorithms along with Jeff Hinton back in the 80s. Computers were really, by today's standards, very, very puny, right? And now computers are millions and billions of times faster, more computing power. And it turns out that by expanding the size of the network, the number of connections, the weights, it scaled extremely well. The bigger the network, the more the layers, the better the performance. And that takes more and more flops. And, we're talking about, when I did a particular project called NetTalk, which was text to speech, I trained a network to pronounce English words, which turns out to be very difficult, because there's regularities and exceptions. And that network had 300 units and 30,000 connections, weights. That actually, for the time, was very large. But today, there are literally trillions of weights, trillions, right? It just gives you a sense for the scale. And without the Moore's law, which is the doubling every year, every 2 years of the computing power for the same amount of money, we wouldn't have been here. So this is really what's driving it. The flops.
Just some technical terms quickly: higher dimensional math, networks, parameter space. What's the meaning of these kinds of ways of thinking?
Okay, well, we live in a three-dimensional world, right? We're talking about how humans navigate, right? We're first of all, if you're on the Earth, it's 2D, right, with your car. But, if you're flying, it's 3D. Well, these networks live in what's called high dimensional spaces. That is to say, instead of 3, it's literally, trillions of dimensions. And we can't even imagine 4 dimensions, right? So we're very limited in terms of our ability to even imagine what that space looks like. Now, it's very important, because it turns out without having those huge high dimensional spaces, which by the way, you have in your brain. In fact, you have many, many more synapses on the order of a million billion, right? I mean, that goes 100. Let's see, that would be about, I guess, 100 trillion. That is way beyond what's in a transformer, right? So you actually have enormous capacity. Of course, you have a lot more to do, right? You have to survive in the real world. But that just gives you a sense for the numbers that we're talking about here. Now, the other thing is just really interesting is that mathematicians have jumped in, and what they've discovered is that the mathematics of high dimensional spaces is really weird in ways that nobody even before could have thought. That the shapes of things, they're called manifolds. These are subspaces which are used by the transformer and your brain to store things that are not just single items, but whole sequences. You can memorize music, for example. How can you memorize music, right? It's not a label, right? It's a whole sequence of notes and words. And that is something that our brains are really good at. And that's because of what's called manifolds. That's a term from mathematics. And so we're learning new mathematics to understand these transformers.
So how fundamentally do large language modules form an internal representation of their training data and enable it to generalize from specific isolated examples rather than just repeating the isolated example?
Yeah, this is critical. This is what really differentiates the new modern AI from the traditional. In the old days, you had to anticipate every possible thing that could possibly happen, and it blows up combinatorially. That means that there's so many combinations of things that each one has to be explicitly stated and what you do in that case. The beauty of these large language models and deep learning is that you train it on a data set, and it can actually generalize to other inputs, similar inputs that are different, that it's never seen before, right? When you ask a question to ChatGPT, it may never have come across that question before, right? And old AI, would have crashed and said, "Well, I don't know the answer," but the large language model will give you something that is the best possible answer given what it already knows, that it is able to interpolate. That is to say, is able to find nearby answers that are close, that it knows about, but it now is able to generalize to your question, and it does that in a very seamless way. It does, in other words, it just has that all embedded, just like you do. I can ask you a question that you may never have heard before, and you'll think about it, and you'll come up with some answer.
Sure. People critique LLMs by saying they really don't understand sentences. They're just auto-completing sentences, even probabilistically based on a large data set. But to me, that's just the semantics of the word, what understand means and how it comes about. So how do you deal with that?
You put your finger on it, and this is actually something that has, I think, really shaken up the whole world of philosophy and linguistics, and in general, in science, actually. So what it's revealed is that humans actually don't know what it means to understand. Right? There was a debate over at University of California, San Diego, in cognitive science between two professors, experts on the question is, does ChatGPT understand language, right? And, it was a typical debate, back and forth, back and forth. And at the end, they took a vote. Half the audience thought it didn't, and the other half of the audience said yes or maybe. Right? So what that immediately tells you is that if the experts can't agree on something, it means that there's something that is desperately wrong with our current way of using words to try to explain things. If you look up understanding, for example, in a dictionary, what do you get? Well, you get a string of other words. You look those words up in the dictionary, what do you get? Another string. In other words, it's all circular.
Sure.
And in science, you have to ground a word into something that is physical. That is to say, like mass, I can measure it. Energy, I could measure it. Well, how do you measure understanding? Right? There is no gold standard for that. And really, what it reveals is that the word really is a very, very crude way. And look, every animal on the planet that has survived evolution has to understand, in a basic way, things in the world that allow it to survive. Right? It's not human understanding. And similarly, these large language models. In my book, as I said, it's as if an alien landed on the earth and started talking to us in English, right? And the only thing we can be sure of is it's not human. But it has some form of understanding, and the question is, how does that relate it to our understanding? And that really, I think it's really exciting, because it gives us, for the first time, another data point, that in terms of understanding language.
There's been some rumors that large language modules are hitting a ceiling. The major AI companies are said to be seeing diminished returns from their huge investments to build more advanced models. Rumors are that the next-gen versions of OpenAI's Orion and Google's Gemini are not meeting the expectations. So has the scaling law peaked? In other words, the more data you bring in, the better the results will be. But is that linearity or even exponential approach trailing off?
Well, yes and no. Well, first of all, what's the limiting step in training one of these large language models is the data, the words. We've run out of words. They've literally scraped the entire internet.
Yeah.
Books, news reports, computer programs, and now that you need, if you're going to train a larger network, you're going to need more data. And now they're trying to find ways of creating synthetic data, but that's not really as good as real data. So actually, this is good, because what we actually need now is not a bigger model. What we need are many smaller models, right? Now, in other words, there is no human being that has absorbed the world's knowledge. It's in that respect, it's already super intelligent, right, with regard to the amount of information that it has absorbed. But what we really want is higher quality data. And it's been shown that if you have higher quality data, you can actually get better performance on smaller tasks. And now what's happening is, that there's 100,000 AI startups out there, which are taking the open, source models like Llama and Mistral, and applying them to fine-tune them with smaller data sets that are more specific for a particular application. Could be the database of a company, all of the customers and so forth, or it could be in medicine, particular diseases. So this is really where the future is going to be. It's not going to be in bigger and bigger models. It's going to be in a proliferation of smaller, more focused models, but with the same capabilities, but digging deeper into the particular problem.
Given the future is in these targeted LLMs to specific tasks, what then is the holy grail of AGI, artificial general intelligence, and how would we recognize that we've achieved it?
Well, there is, in addition to answering questions, there's something that I call self-generated activity in your brain. In other words, when you go and there's no sensory input, your brain is still ticking over, right? You're thinking, you're planning, you're maybe thinking back in the past or the future. When you stop talking to one of these ChatGPT models, there's nothing in it. It just stops. Zero, right? There's no internal activity. So that's an example of something that is missing, is desperately missing. If we really want to be able to have it closer to how our brains work.
Okay, so another term you've used is superintelligence, and I think by having the vast amount of data that it can call up, that in one sense of the term is superintelligent. But the way I think we would think about it is that a real superintelligent would be an AGI system.
Well, so you're right, and the self-generation produces things like reasoning. How you reason through a sequence of steps in order to be able to come to a conclusion. And that's very difficult for these large language models. You can train it to some extent. It's called chain of thought, but it doesn't have the flexibility or the general nature of the way that our brains are able to take a problem apart into pieces and be able to solve them, divide and conquer. That's going to come. I mean, we're working on that. But it's still a limitation right now. So it's amazing how far you can get just with this automatic part. By the way, you're not consciously aware of things that are automatized that you're doing, without thinking, and basically these large language models are stuck in that state. They don't really have access to what they're saying the way we do.
So what would be the data point or the set of data points that you would see that you would then say, yes, this LLM has AGI?
Well, I think that, for example, one of the things that we're really good at is to be able to understand other human beings in a deep way, and be able to form what is called theory of mind.
Theory of mind.
Yeah, and it actually evolved probably from the ability that we have to sort of think about ourselves, self-consciousness, right? And so really, that's the kind of level. So it's called System 2 in AI that's missing. And in the human brain, we there, in addition to all of the automatic stuff, right? When you go offline and start thinking, right, internally, self-generated, that's what's going to create, what you might call as AGI. I think AGI is a very kind of, it's like understanding. It's not well defined. Right. So we'll know when we see it.
Terry, this has been terrific. I thoroughly enjoyed it. I love the book. It's a very important book. I recommend it to everyone. ChatGPT and the Future of AI, the Deep Language Revolution. My only request for you is please let's not wait another 20 years between our Closer to Truth conversations.
Well, I greatly enjoyed our discussion, and I assure you that we will talk before then.
Great. Viewers can watch over 1,000 videos and TV episodes on consciousness on the Closer to Truth website and Closer to Truth YouTube channel, mind-body problems, brain function, free will, personal identity, creativity, panpsychism, dualism, idealism, parapsychology, life after death, cosmic consciousness, all infused with critical thinking. Thanks, everyone, for watching. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing. Closer to Truth is now accepting your tax-exempt donations. Please come to closertotruth.com/donate. Thank you very much for supporting us, and thanks for watching.